Thank you. Dynamic shift registers, I'm sure you have also studied in your that pulse and digital circuits course. But I will just discuss in view of the new things I've highlighted in this course regarding MOSFETs. So this is the starting point. In fact, we shall gradually switch over to dynamic logic. And it is found that for the case of single channel inverters, single channel MOSFETs is the shift registers whose dynamic version is most natural. So therefore, I'll start with dynamic shift registers using single channel transistors, nMOS, not CMOS. But it is applicable to CMOS also. But we shall discuss that afterward. Dynamic shift registers, there are two approaches. One is called ratioed logic approach. Ratioed logic. And the other is ratioless. Normally, when we consider a shift register, we use either JK flip-flop or D flip-flop and two stages for master-slave operation. You remember that? And the number of transistors which are required will be more than, that is why dynamic logic has come, simply to minimize the size of the logic. That means the transistor count in the IC, so that ultimately you can get very high packing density. And also we shall see just today that if we can do something to reduce power dissipation. So two things are there, two motivating factors are there beyond dynamic logic. One is higher packing density, that means lower transistor count. And second is, we shall see that whether we can reduce power dissipation. And thirdly, of course, whether the speed can be increased. Anyway, whenever any digital logic, these are of primary interest to us. One is the higher packing density from VLSI point of view. It reduces a lower standby power. You know that for single channel cases, the power dissipation is maximum during standby, which I'll discuss after already. And so minimum standby power dissipation. And thirdly, I want to increase speed. Okay, and we shall see just now, while discussing the dynamic shift register, that all these things can be achieved in the dynamic principle rather than from the static principle. Only at the cost that such logics will not operate below a certain frequency. We shall say that. Below a certain clock frequency, it will not work. To start with the simplest one, which is the ratioed logic, we shall discuss two approaches. The simplest approach with this is with just by using the steering gates. Sorry, I have not drawn properly. You see that here there is nothing but these are called inverters with steering gate. This is an inverter. These are all inverters, simple single channel NMOS inverters. But at the input of each inverter, I have a MOS switch. These are called transmission gates or switches, pass transistor, whatever you call it. Only thing is what I have done is that at the gates of these switches or transmission gates, I have connected some clocks, clock signals. I have called them phi 1, phi 2, phi 1, phi 2. These clocks are called two-phase clocks, two-phase non-overlapping clocks. So phi 1 and phi 2 are two-phase non-overlapping clocks. They look like this. Like this. So this is your phi 1, this is your phi 2. Please remember this is the 0 state and this is the 1 state. the 0 state, these are 1 state. That means when phi 1, you can easily see that the clocks are so schemed, so phased. That is why called two-phase non-overlapping clocks. Non-overlapping, there is this one state does not overlap. One state of this clock and the one state of the other clock, there is no overlap between them. And you have to ensure that properly. And in that case, you can easily say that when phi 1 is high, phi 2 is low. This when these transistors are on, the other transistors will be off, and vice versa. When these transmission gates are on, closed, the other transmission gates will remain off, open. So what I am doing simply, suppose I apply some signal in the forms of ones and zeros, the digital signal, a word, 1001 sequence. Then, according to my clocking scheme, this signal will pass through this, down these transistors, and we expect to get a one-digit shift, one bit shift, with respect to the input signal at this. This is the input, and this is the output for the one stage, single stage shift register. Okay, and how many transistors you have used here? 6. To realize this master slave, we shall see that how it is master slave. I'm sure you have studied this. I know that it was taught in your pulse and digital course to some extent, but we shall discuss it in a little bit more detail here. So you see that there are 2 stages, and we have used only 6 transistors to realize this. To achieve the same thing using JK flip-flops, how many transistors will be needed? How many gates are involved in each stage of JK flip-flop? Means JK master slave. I mean master slave JK or D flip-flop. In the form of NOR gates, you think, because that is convenient in MOS technology. 4%. Steering gate, then latch, first steering gate, two NOR gates or 2 NAND gates, whatever the case may be. Then the actual latch, and if necessary for preset set and overriding, clock overriding preset set operation, another 2 AND gates or OR gates intermediate. You remember that. This forms one half stage. Half stage means either the master or the clock, whatever the master or the slave. And if we combine them, the number of transistors count will be much higher than that in this particular case. So that is one benefit. We shall discuss gradually what are the benefits. One benefit already achieved is the transistor count here is considerably less than that in the case of static. Those are static. Conventional one. I would not say static and conventional one. And here what we are doing, we are using a special clocking scheme and facial configuration to transmit the signal bit by bit, and with a single 1 bit delay or 2 bit delay or 3 bit delay as we go down the chain. Okay? How it is done, I think you'll remember that. Already it was discussed in your class, but you can remember. And this is why it is called ratio logic. Because these inverters are standard inverters, there is nothing new. So I have to maintain that for this kind of configuration, I have to maintain that 1:1 and say 50:1. That kind of ratio I have to maintain. These are standard. And if you use that HMOS kind of principle where this transistor is a depletion mode, then simply you have to connect it here, and this may be 1:1, but this will be around 5:1 or 4:1. There will be some saving. But still, it is a ratio logic, and as a result, your packing density will be affected, power dissipation will be more. You can't avoid it. That is why this ratio logic suffers from those standard drawbacks, which I've already discussed in the class, and this shape register also is going to suffer from those standard disadvantages. Example, one is packing density, the second is power dissipation, and automatically with that, speed is also linked up. If I can do something, we shall see afterward that we can improve upon all these factors. We shall see in the case of ratio-less design. This is ratio logic. Unfortunately, because of I cannot use a very big space, there will be some difficulty in explaining the operation. But let us see, there is no problem. I am drawing the clock once again. Suppose, let me consider a signal like this. It's a sequence of 0, 1, 1, 0, 1, 0, 0, kind of any arbitrary signal at the input at this point. We shall now, this is what is known as timing diagram of a logic. Timing diagram. This is what is called timing diagram. You will now, today I think you have heard of logic simulators, logic simulation modules, the programs available. So there, this timing diagram can be very easily obtained. You don't have to do anything. You define any signal at the input for any complicated digital system, and you can find out what will be the waveform at different points down the system. But here we are trying to draw it just by using our logic. Suppose I have applied such an input sequence 0, 1, 1, 0, 1, 0, 0 kind of sequence at this input point. We want to see what is happening at the points A, B, B dash, C, etc. And at this point C, I expect a 1-bit shift of this input signal. Let us first consider the point A. What is going to happen? Suppose the input is 1. When phi 1 is 0, the A point will remain in the earlier state. If it is 0, it will retain 0 state. If it is 1, it will retain 1 state, because this is off. And this is a MOS capacitor with a very, very high leakage resistance. This is off means also its leakage current. That is the advantage of MOSFET. Its leakage current is extremely small, of the order of nanoamperes. Therefore, effective resistance seen between this point and ground, between A and ground, when phi 1 is 0, that means this transistor is off, is very, very high, usually of the order of several megaohms. So what will happen? If any charge is present here, that will be retained for some time. If you don't exceed a lot of time, then you are in trouble. But if you can't come, if your clock frequency is below a certain, is higher than a certain value, then there is no problem. The level at any point will be retained for over that period of time, called clock duration, clock period. So if it is 1, when phi 1 is 0, A will remain in the earlier state. But when phi 1 becomes 1, this 1 will be very faithfully transmitted. And immediately you have seen that the clock pulse is so configured that normally these are narrow pulses. These are not wide pulses. So the 1 will be only for a short, that means these switches will be turned on only for a short duration. Therefore, most of the time the switches will be remaining off. So if whatever may be the state, only state change will take place during only the switching of this MOSFETs, and I have to, of course, the clock duration, the width of the clock pulse have to be decided. It depends on the MOSFETs. If it is designed for a very high-speed logic, then naturally you can use very narrow clock pulses. But at the same time, if it is meant for very ordinary applications, you may need clock pulses of duration, say pulse width, say typically of the order of 100 nanosecond or 500 nanosecond kind of thing. But in certain cases, you can play with 1 nanosecond, even less than a nanosecond. Please remember this. So it will be turned on, and then this input, whatever may be the input, will be just inverted at this point because there is nothing here. It's plain inverted. In the same way, this signal will be transferred to this point depending on phi 2. And it will be further inverted here at this point. And that's how I can draw the timing waveform, the timing diagram of voltages at A, B, B dash, etc. You do it yourself. I am also trying. Let us see what is happening at A. You see that one important thing to be noted, that the signal should be at least in synchronization with one of the clocks, because the signals, after all, is derived from some other logic, and that is the synchronous logic. The signal cannot have any transition at any arbitrary point. It will be always synchronized with one of the clocks. In this case, I have shown that it is more or less synchronized with phi 2. You have seen that transitions are taking place here, 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 etc. It could be with phi 1 also. All right? So exactly, I have not drawn it arbitrarily. This is very important because the signal is derived from some other logic, synchronous. With the same clock they are working. So you try to draw for A what is going to happen. What is going to happen at A? You see that at this point, there is a clocking transition for phi 1. And then input is 0. And if at the earlier state input was 1, I do not know, then it will be switched, it will be 0, because suppose in earlier state it was 1, but then because input is 0 means it's grounded. When phi 1 is high, it is providing a short circuit, therefore this charge will be discharged. The capacitor at this node will be discharged and it will turn to 0. And therefore, at this point, we expect, suppose initially there it was at 1. I do not know. It was either at 1, it depends on the sequence. It depends on the sequence. It is either at 1 or 0, but let us assume it 1. But then it will turn to 0. Then I have to wait up to this time. Please see that. I have to wait up to this time. Phi 2 does not have any effect on this thing. At this instant, you see that input is high, and the clock is the transistor, this MOSFET is on. So naturally, it will charge to the high voltage, the 1 state, and it will remain 1 for a short duration here, because but then thereafter, what is going to happen? When this is off, when phi 1, after this very short time, phi 1 again gets off. Phi 1 becomes 0 means this transistor is off. So what will happen? This voltage will be just kept, will be retained, because that is why it is called dynamic logic. It is working under dynamic condition. So it will retain that one state, and I have to wait up to this time when another clocking transition is taking place, and then also input is high. At this instant also input is high. You see that our input sequence is such that at this instant, the next clocking transition for phi 1, input is high. Then in that case also therefore the high state will be maintained, and I have to come up to this time, it will retain here. Am I correct? But now, during this clocking transition, the input is now 0. So it must go down to 0. All right? Then I have to wait up to this transition. It will maintain that. But now again input is high, and it will pass. It will go like this. I have to wait up to this clocking transition. But then again it is 0, like this. And similarly, when I'm here, this is also 0. Am I correct? Is it all right to all of you? So where is the dynamic logic principle is holding here? Simply during the periods when phi 1 is 0, this state, whatever was the voltage developed at the node A, that will be retained. Suppose if I go on increasing the clock duration, clock period, that means reducing the clock frequency, then what is going to happen? Do you think that these lines will be perfectly horizontal? No. They are discharging, but with a very, very large value of RC time constant. Actually speaking, this is an exponential decay. But this time is so short compared to that RC involved that I am practically getting it horizontal. And that I want. That I want. Therefore, what is the most important thing to be needed is that our technology should be very, very perfect. The MOS capacitor, the MOSFET dielectric should have a very, very high resistivity. The MOS gate dielectric should have a very high resistivity, so that the resistance of the MOS capacitors will be very large. Similarly, the junctions will be very less. You see that it is not only the MOS capacitor here, but also the drain substrate junction that is coming into picture. And if that junction is leaky, then your advantage is going to be lost. Therefore, the MOS technology, the material should be very good. That is very, I think I have mentioned in the device class as well as in my discussions in this lab, in this particular course, that if you want to have a very low, leakage of the PN junction, the material should be very good, because it is the traps through which it has been found, it can be shown that whenever you reverse bias a junction, the leakage current depends on what? When you reverse bias a PN junction, on what parameters the leakage current depend? One is the doping concentrations on the other side. You know that the leakage current is entirely contributed by the minority carriers. If the two sides are relatively heavily doped, the minority carriers are less, therefore the current will be less. This is one thing. But then what are the other things? When these minority carriers are passing through the depletion layer of the reverse bias junction, which has got a very, very high field inside. Let me repeat. When a PN junction is reverse biased, the minority carriers pass across the junction and they pass through the depletion layer at a very high speed because of the very high built-in electric field in that region. Built-in depletion layer has got a very high field. So what is going to happen in that case? Yeah, it will happen that effective number of electrons and holes, because they are not present in the depletion layer for a long time. So the PN product, the product of Pn in the depletion layer will be very, very less compared to Ni squared. And I think you know that if Pn is equal to Ni squared, the semiconductor is in thermal equilibrium. If Pn is more than Ni squared, due to some reason, there will be recombination, as happens in the case of bipolar transistor. When electrons are injected in the base region, Pn is more than Ni squared, there is recombination. But in this case, Pn is very much less than Ni squared. So what is going to happen? There will be generation. Excess electron hole pair generation due to transfer of electrons from the conduct valence band to that is what is known as Shockley-Reed-Hall SRH recombination generation theory. If Pn is in more than Ni squared, recombination will dominate. If Pn is less than Ni squared, generation will dominate. Whereas if Pn is equal to Ni squared, the recombination rate will exactly be balanced by the generation rate, and therefore a steady number of electrons and holes. Thermal equilibrium case. So what is going to happen now? When these carriers are passing through the depletion layer at a very high speed, the effective Pn product in the depletion layer is very small compared to Ni squared. So there will be a lot of generation. And these generations is enhanced. I mean, generation recombination rate is enhanced if there are traps in the valence in the band gap. Traps means some energy states contributed by impurities, defects, etc. So generation rate is enhanced. Generation recombination rate is enhanced by the presence of traps. So what happens if those very few minority carriers are traveling? Ultimately, there may be a lot of electron hole pairs generated due to the enhanced generation mechanism via the traps, and you may get a large leakage current. But you don't want it here. We want that this drain substrate junction, which is reverse biased, should give you a very, very low leakage current in order that it becomes a very successful dynamic logic. Therefore, there is a very important thing to keep in mind, that the material, the silicon material for VLSI MOS should be very, very good compared to the bipolar material. The bipolar transistor fabrication, the basics raw material, the silicon substrate, can be tolerated to a certain value. Of course, I am speaking of not very advanced bipolar, medium advanced bipolar. But compared to MOS, as soon as you consider dynamic logic, the material comes in and it should have very few traps inside. This should be kept in mind. There is nothing great in it. Only things should be kept in mind. That is why this junction leak, it is not only the MOS capacitance should be, but also the junction leakage, both are important in order that it is a very good dynamic logic. Please remember this. Next, come to the other point. You see that coming to B, it is simply the inverted one. Quite all right, there is no problem because this is an inverter. So these ones have been converted into zeros. Coming from A to B, ones have been converted into zeros, and zeros have been converted into 1. There is no problem. Similarly, I can go to B dash point using the same logic. Just try to do it yourself. You try it yourself, then see the diagram. Don't look at here. Try it yourself, then look at this diagram, whatever I'm drawing. you see that while drawing B dash, the waveform at B dash, it is the same thing. Input here is equivalent to B and A here is equivalent to B dash. Only thing is clock has changed from phi 1 to phi 2. So you use the same principle. And you see what has happened at this. So I have to now consider phi 2 and not phi 1 clock, phi 2 and not phi 1. So you see that I have to, at this transition of phi 2, B is high, so input will also be, B dash will also be high, okay? And it will continue till the next pulse comes, next clock comes, when B is now 0. So automatically B dash will also be 0. I have to wait up to this instant. Here also B remains 0, so it will continue to remain 0. Output B dash will also remain 0. Then at this transition, B is now high, so B dash is also high. It will continue up to this instant. And now B is 0, so it is 0. Then you go to up to this instant. It is 1, so it goes to 1. Straightforward, nothing, there is nothing special in it. And C will be just the inversion of that. You just see the inversion of that. And you see that I have got a sequence, I have got back the sequence 0, 1, 1, 0, 1, 0, 0 type of thing. 0, 1, 1, 0, 1, 0, 0 type of thing. Only thing there is a shift by 1 bit. So one thing, let me ask you, do you expect that, say, you see that when phi 2 is phi 2 goes high at these different instants. Suppose here at this instant phi 2 goes high and B was B was high. Let us consider not that instant. Another instant. Yeah, at this particular instant, for example, this transistor is on. Okay, at this instant, this transistor is on. You see that B was high, and I have assumed that B dash will also remain high at the same level. High at the same level. Please try to understand this. High at the same level. I have drawn it in such a way that at this instant, you see that before this instant, B was high, and then the switch is on. I have maintained the same level here. Is it correct or not? It is not correct. So that I have not shown. In fact, there will be a little fall, because this is an ordinary, that is a drawback of this kind of switch. But if you replace it by a CMOS transmission gate, that problem will not be there. So there will be a slight fall, not very slight, in fact around 1 volt fall. If it is a 5 volt thing, around 1 volt fall at this point, but not at many ways. At those points where charge sharing is taking place. Please remember this, this has to be kept in mind. So this ratioed logic, as we can conclude therefore this particular design, here using the clock, inverters are remaining as it is. You know, there is a lot of standby power dissipation here. When VDD is, because all the supplies are straightforward from VDD. Okay, this is one thing, and these switches are kept permanent. This is on, always on, isn't it? The load transistor is always on, because this has been kept in saturation here, or it could keep it in depletion mode if the device was depletion mode MOSFET, which I have discussed earlier. But this is always on, therefore the chain current in the inverters will be, most of the time, so long as this transistor is on, so long as this transistor is on, the chain current will flow, and the power dissipation, it can be shown that when it is not using, in most cases, the standby power dissipation will be quite appreciable. Can I do something to prevent that? This is a ratio logic concept, I agree. I have increased the packing density and all these things I have achieved. But what I could not achieve is, firstly, the main drawback of ratio logic, the ratio has to be maintained. And secondly, the power dissipation is quite high. Can I do something to reduce the power dissipation? Maybe speed I cannot play much, but power dissipation, and that I shall present in the next scheme. Ratio logic, but with a different kind of scheme. Let us see that. The clocking, only thing is this is the same. This is again ratioed logic. So it is a ratioed logic with a different clocking scheme. Earlier case, you remember, it was only the transmission gates which were switched on and off by the clock pulses. But now it is not only that this thing, but also the load transistors also are coupled with the same clocks. So the switching on and off of the load transistors are also performed by the clocks. And you remember that I have used narrow clock pulses. Therefore, the load transistor will be switched on only for short durations. Most of the time, the load transistor will go off. So what? The standby power dissipation will be automatically reduced to very low level. There is a great advantage there, but let's just see how it works. You can try yourself, the same kind of thing, you just try yourself. Try yourself. I am also trying. you see that I think I will discuss in the next class, but before I round up today, already time is over. You just note down the small changes in levels. I think you have understood this timing diagram, but only note down the small changes in levels at C as well as at B, and try to explain. We shall